the last star in the universe will go dark in roughly 100 trillion years, and that will not be the end. Not even close. Subscribe if you want more of the cosmos. This is Whitespace. Settle in, consider a question so simple it sounds almost childish. What happens after everything is gone? Not the end of a civilization, not the death of a star, the end of everything, every atom, every photon, every quantum of interaction. A universe that has run its full course, expanded to the point where the distance between particles exceeds any meaningful scale of interaction, cooled to temperatures indistinguishable from absolute zero, and settled into a state of maximum disorder. Physicists call this state maximum entropy, and the strange thing is, it may not be the end of the story at all to understand why we need to sit with the concept of infinite time. Human intuition is not equipped for this. We speak of billions and trillions of years as though they are large numbers, and by any everyday standard, they are. The current age of the universe, 13.8 billion years, is already beyond direct comprehension, but infinity is not a large number. It is a different category entirely. Given infinite time, events do not merely become probable. They become inevitable, and not just once, but an infinite number of times. This is the territory that the Austrian physicist Ludwig Boltzmann entered in the 19th century. Boltzmann had built much of the mathematical foundation of thermodynamics, and one conclusion followed unavoidably from his equations. A closed system left to itself will always drift toward greater disorder. Heat spreads, structures dissolve, order gives way to randomness. A glass of ice water left alone reaches room temperature. A complex molecule unattended breaks apart. This is the second law of thermodynamics, and it is one of the most firmly established principles in all of science. And yet Boltzmann recognized something deeply counterintuitive hidden within his own framework. Even in a system at maximum entropy, the constituent particles never stop moving. They fluctuate, they redistribute. The laws of physics are, at the microscopic level, time-symmetric. Nothing in the equations prevents particles from spontaneously organizing themselves into ordered configurations. What prevents it in practice is probability. An ordered state is vastly less likely than a disordered one, but vastly less likely is not the same as impossible. Given enough time, genuinely infinite time, any configuration of particles that is physically possible will eventually occur. Not just once, an infinite number of times. To appreciate what this means, consider a sealed container filled with gas molecules, each one in constant random motion. If you watch that container for long enough, you will see the molecules drift from one configuration to another. Most configurations look like a uniform blur, molecules spread evenly throughout the volume. But occasionally, by pure statistical chance, a small cluster will form in one corner, a slightly denser pocket, a local reduction in entropy inside a system otherwise dominated by chaos. Nothing forbids this. The equations of physics permit it, and in infinite time, it will happen. This principle has a precise mathematical statement, known as the Poincare recurrence theorem. It states that any bounded physical system will eventually return to a state arbitrarily close to its initial configuration, given enough time. The time scale involved is staggering. For a system the size of even a modest volume of gas, the recurrence time exceeds any number with a convenient name. But the theorem is exact. Given infinite time, the return is guaranteed. Now extend this logic to the scale of the cosmos. After every black hole has evaporated through Hawking radiation, a process that itself takes longer than 10 to the power of 67 years for stellar mass black holes, and incomparably longer for the supermassive variety. After every proton has undergone whatever slow decay process the underlying theory of particle physics permits, after the last possible nuclear reaction has occurred, and the universe has reached a state of cold, featureless equilibrium, the fluctuations continue. Elementary particles, quarks and leptons, still drift through the void in their quantum mechanical way, and over timescales measured not in billions or trillions, but in numbers with 50 or 100 zeros, statistical accidents will happen. An apple might spontaneously assemble from random quantum fluctuations, a human hand. A complete and functioning human brain with a lifetime of memories and a subjective experience of consciousness, appearing from nothing in the middle of an otherwise empty universe, persisting for a moment and then dissolving back into disorder. This is the Boltzmann brain, a concept so strange that its name sounds like a joke, and yet it follows logically from the combination of statistical mechanics and cosmological theory. The physicist Andrei Linde, one of the architects of inflationary cosmology, pointed out the full weight of the paradox. If the universe is infinite in extent or infinite in duration, then random fluctuations will produce disembodied conscious observers far more often than the slow process of cosmic evolution, stars forming, planets condensing, life emerging over billions of years of biological refinement. The number of ways to produce a fleeting fluctuation containing one mind vastly exceeds the number of ways to produce a planet-sized nursery for that mind. And if that is true, the odds strongly favor any given conscious observer being one of these fleeting statistical accidents rather than a creature with a genuine causal history. Linde put it plainly, the logic of quantum theory and inflationary cosmology forces him to accept that infinitely many copies of his own consciousness will eventually emerge from the vacuum of a distant future universe. And if that is the case, why should he trust that he is the original? This is not a question with a comfortable answer. It is one of many places where cosmology leads not to clarity, but to a kind of structured bewilderment. The sensation of pushing at a door and discovering that the room on the other side is larger than the building. Nietzsche's concept of eternal recurrence, developed from purely philosophical grounds in the 19th century, arrives at a structurally similar conclusion: that the finite number of possible configurations of a finite amount of matter, played out over infinite time, must repeat. The physicist and the philosopher, separated by discipline and by method, find themselves standing in the same strange place, but the Boltzmann brain paradox conceals an even deeper puzzle, one that physicists call the problem of the arrow of time. Consider this. Every fundamental equation in physics, Newton's laws, Maxwell's equations for electromagnetism, even the equations of quantum mechanics, is perfectly symmetric with respect to time. Run the equations forward, they describe the universe as we know it. Run them backward, they remain equally valid. Nothing in the mathematics forbids time from flowing in reverse. And yet it doesn't. Ice melts, eggs break, people age. The direction from past to future is unmistakably real in experience, even though it appears nowhere in the underlying laws. The resolution, most physicists believe, lies not in the laws themselves, but in the initial conditions of the universe. The Big Bang produced the cosmos in an extraordinarily low entropy state, extraordinarily ordered by the standards of all the configurations matter could in principle occupy. From that low point, entropy has been rising ever since, and will continue rising until maximum entropy is reached. The direction we call forward in time is simply the direction in which entropy increases. We remember the past and not the future, because the past is the lower entropy end of our local region of time, and brains, like all ordered structures, are sustained by the flow of energy from low entropy sources toward high entropy ones. This explanation is mathematically coherent, but it raises an immediate question. Why did the universe begin in such a low entropy state? Why did the Big Bang produce so much order, when a randomly chosen initial configuration would almost certainly have been far more disordered? No one has a fully satisfying answer, Some physicists argue that a low entropy beginning is required by the anthropic principle. Only in universes that begin ordered can observers form to ask the question. Others propose that the ultimate explanation must involve a theory of initial conditions that goes beyond anything currently available. For now, the arrow of time points from a mysterious ordered beginning toward an inevitable disordered end. And the reason for that beginning remains one of the most profound open questions in all of science. The universe is not just vast, it is organized at scales far exceeding anything human intuition was built to handle. Our galaxy, the Milky Way, is itself an enormous structure, a disk of roughly 400 billion stars spanning 100,000 light years. But within the observable universe, it is unremarkable. One galaxy among an estimated 2 trillion. And those galaxies are not scattered randomly. They form a cosmic web of filaments and sheets and clusters, separated by enormous voids, all of it shaped by the interplay of gravity and the initial conditions set at the moment of the Big Bang. The architecture of this web is not accidental. Its origins lie in tiny quantum fluctuations that existed in the earliest moments of the universe. Variations in density so small, they were imprinted at the scale of subatomic physics and then inflated to cosmological size during the epoch of rapid expansion that cosmologists call inflation. Those fluctuations became the seeds of everything. Regions of slightly higher density attracted more matter through gravity, grew denser still, and eventually collapsed into the first structures, dark matter halos that served as scaffolding for ordinary matter, which fell inward, heated, and ignited as the first stars. The cosmic web we observe today is the fully grown version of a pattern that was determined in the first fraction of a second after the beginning. And this is where the concept of dark matter earns its central place in modern cosmology. Dark matter does not emit light, does not absorb light, and does not interact with the electromagnetic force at all. It is detectable only through its gravitational effects. Yet without it, the observed structure of the universe cannot be explained. The galaxies we see would not have formed as quickly as they did. The rotation curves of galaxies, the relationship between orbital speed and distance from the galactic center, would look different. The way that light from distant objects is bent by the gravitational fields of intervening galaxy clusters would yield different measurements. Every line of evidence points to the same conclusion. Roughly 85% of the matter in the universe is made of something we cannot directly observe. What that something is remains unknown. The leading candidates have included weakly interacting massive particles, WIMPs, which would interact with ordinary matter through the weak nuclear force and gravity, and would have been produced in great abundance in the hot early universe. Underground detectors filled with ultra-pure xenon or germanium shielded from cosmic rays by kilometers of rock have searched for the signature of a WIMP striking an atomic nucleus. No confirmed detection has been made. Actions, originally proposed to solve a separate problem in particle physics, have also emerged as candidates, and experiments hunting for them using strong magnetic fields and microwave resonators are underway. Primordial black holes formed in the extreme density of the early universe before any stars existed, represent another possibility, one that does not require any new fundamental particles. The failure to directly detect dark matter particles, despite decades of increasingly sensitive experiments, has not shaken the conviction that dark matter exists. The gravitational evidence is too overwhelming. The bullet cluster, a pair of galaxy clusters that passed through each other roughly 150 million years ago, provided one of the most direct confirmations. The hot gas of the two clusters, which constitutes most of the visible matter, collided and slowed down, remaining near the center of the collision. but the dark matter in each cluster, detected through gravitational lensing of background galaxies, passed through the collision without slowing, separating cleanly from the gas. The separation between where the mass is concentrated and where the visible matter is located is precisely what dark matter predicts, and what no alternative gravity theory has satisfactorily reproduced. Alongside dark matter, the early universe left a second kind of imprint in the large-scale structure we observe today, one that encodes the history of sound itself in the first few 100,000 years after the Big Bang. The universe was a hot plasma of protons, electrons, and photons, so dense and energetic that light could not travel freely. Pressure waves, sound waves, in the most literal sense, propagated through this plasma at enormous speed. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, the plasma became transparent, and those sound waves froze in place, their final position locked into the distribution of matter for all subsequent time. The signature of those ancient sound waves, called baryonic acoustic oscillations, is detectable today in the statistical distribution of galaxies across the sky. Galaxies are slightly more likely to be separated by a specific distance, roughly 500 million light years, because that is how far the acoustic wave had traveled when the plasma froze. This preferred separation acts as a cosmic ruler, a known physical scale imprinted in the universe that astronomers can use to measure how space has expanded at different epochs. By mapping millions of galaxies and identifying the acoustic peak in their distribution, cosmologists can trace the expansion history of the universe with high precision and test whether dark energy has remained constant over billions of years or has changed. What strikes observers is that the large-scale structure is moving. Every galaxy has what astronomers call a peculiar velocity, a motion relative to the overall expansion of space. The Milky Way, along with the Andromeda Galaxy and the dozens of smaller companions that make up our local group, is hurtling through space at roughly 600 kilometers per second relative to the cosmic microwave background. Something is pulling it, and for decades identifying that something occupied a significant portion of observational cosmology. The answer came in layers. First, the presence of a massive concentration of matter was inferred from the motion of nearby galaxies, a region initially called the Great Attractor, hidden from direct optical observation behind the dense plane of the Milky Way itself. This obscured region, known informally as the zone of avoidance, blocked visible light but not X-rays or radio waves, and advances in those wavelengths gradually revealed what lay behind it. What lay behind it was larger than anyone had initially expected. The true gravitational engine proved to be the Shapley supercluster, a vast concentration of thousands of galaxies centered about 650 million light-years from Earth in the direction of the constellations Centaurus and Hydra. In the late 1920s, the astronomer Harlow Shapley had already noticed an unusual overdensity of galaxies in this region of the sky, mapping tens of thousands of them using photographic plates taken with telescopes in South Africa. It was not until 1989 that this supercluster was formally recognized and named in his honor. The Shapley supercluster's mass, some 10,000 times that of the Milky Way, is sufficient to influence galactic motions across an enormous region of space. The Great Attractor itself accounts for roughly 44% of our local group's peculiar velocity. The remaining motion points toward Shapley. An entire river of galactic movement, flowing across hundreds of millions of light years, converging on a structure that was barely detectable until modern X-ray observatories finally pierced the obscuring dust. And Shapley in turn is part of an even larger structure, the Laniakea supercluster, a gravitationally coherent volume spanning 500 million light-years and containing roughly 100,000 galaxies with a combined mass of approximately 100 million billion solar masses. Laniakea was only fully mapped in recent years when astronomers constructed a detailed three-dimensional velocity field of the local universe and identified a basin of gravitational attraction, a cosmic watershed, into which galactic flows converge the way rivers drain toward the sea. The name comes from the Hawaiian words for immeasurable heaven, chosen to honor the Polynesian navigators who crossed the Pacific Ocean using nothing but stars and wave patterns. Determining the mass of such a structure is not straightforward. The naive approach, counting galaxies and multiplying by the mass of a typical galaxy, fails immediately. Because the mass between galaxies in the form of hot ionized gas and dark matter exceeds the mass contained within the galaxies themselves. The largest structures in the universe are young in a cosmological sense. They formed most recently and have had the least time to settle into stable configurations. This makes their mass difficult to measure precisely, and their ultimate fate difficult to predict. The deeper you look, the larger the structures become, and the larger the structures become, the more unsettling the questions that arise. One of those questions concerns the horizon of the observable universe. It would be natural to assume that with a large enough telescope, we could see as far as we wished. But the universe has a finite age, and light travels at a finite speed. Looking out into space is the same as looking back in time. The star Deneb, visible to the naked eye in the summer sky, shows us light that departed approximately 2600 years ago. The galaxy Messier 87, located about 53 million light-years from Earth, shows us a universe as it existed long before complex animal life appeared on Earth. And the farthest signal we can receive, the cosmic microwave background, is the thermal afterglow of a universe less than 400,000 years old, stretched by cosmic expansion into microwave frequencies almost unrecognizable as light. Imagine a vast plaza filled with thousands of people. At precisely noon, every person shouts a single word simultaneously. But the speed of sound in this thought experiment has been reduced to 1 meter per second. You shout, and immediately your voice is gone. But 1 second later, you hear the shout of the person standing 1 meter away. 2 seconds later, the person 2 meters away. A minute passes, and you are still hearing shouts from people 60 meters distant, people who cried out at noon and have long since fallen silent. You are hearing not what is happening now, but the record of a single moment arriving in sequence across time and distance. This is precisely the situation with the cosmic microwave background. The radiation we detect today was emitted throughout the universe at a specific moment, roughly 380,000 years after the Big Bang, and has been traveling toward us ever since. Beyond that surface of last scattering, we cannot see, not because there is nothing there, but because the universe was opaque before that moment. The observable universe has a horizon defined not by the size of space but by the age of time. And yet this horizon itself is moving. The universe is expanding and not at a constant rate. In 1998, 2 independent research teams studying the brightness of distant type Ia supernovae discovered something that nobody expected. The most distant supernovae appeared slightly fainter than models of a decelerating universe predicted. Space was not slowing down under the influence of gravity. It was speeding up. The expansion of the universe is accelerating. This discovery implied the existence of a component of the universe with negative pressure, something that acts oppositely to gravity on the largest scales, pushing space apart rather than pulling it together. Cosmologists call this component dark energy, and according to current measurements, it constitutes approximately 68% of the total energy content of the universe. Ordinary matter, atoms, molecules, everything made of protons and neutrons and electrons contributes only about 5%. Dark matter accounts for roughly 27%. The universe we can touch and see is a thin layer of foam on the surface of a much larger ocean whose nature we do not understand. The simplest mathematical description of dark energy is the cosmological constant, a fixed energy density assigned to empty space itself, present even in a perfect vacuum. Einstein introduced this term into his equations of general relativity in 1917, then abandoned it, then watched it return from the dead when the supernova data came in. The cosmological constant fits the observations well, but it creates a profound theoretical problem. Quantum field theory predicts that the vacuum should have an energy density arising from quantum fluctuations, virtual particles constantly appearing and disappearing throughout space. When physicists calculate the magnitude of this vacuum energy, the answer comes out roughly 120 orders of magnitude larger than the observed value of the cosmological constant. This is the worst prediction in the history of physics, and understanding why the cosmological constant is not enormous, or why it has the particular small value it does, remains entirely unsolved. Alternative proposals exist. Quintessence imagines dark energy not as a fixed property of space but as a dynamical field, something like an extremely diffuse fluid that permeates the universe and whose density slowly changes over time. If dark energy is quintessence rather than a cosmological constant, then its strength in the early universe would have differed from its strength today, and this difference might be detectable in the precise history of cosmic expansion. The Euclid Space Telescope, launched in 2023 and designed to map the geometry of the universe with unprecedented precision, will test this over the coming years. This raises an immediate question about the geometry of space itself. What shape is space? In a universe with positive curvature, analogous to the surface of a sphere, two initially parallel lines will eventually converge. In a universe with negative curvature, a geometry analogous to a saddle surface, parallel lines diverge and space extends without limit. A flat universe follows Euclidean geometry at the largest scales. Current measurements of the cosmic microwave background suggest that our universe is either exactly flat or extraordinarily close to it. The curvature, if any exists, is smaller than current instruments can reliably detect. There is also the question of topology, the global shape of space beyond its local geometry. A flat universe could still be finite if it wraps back on itself. If you traveled far enough in a straight line, you would eventually return to your starting point. Patterns in the CMB that repeat in opposite directions of the sky would be evidence of this kind of topology. No such patterns have been conclusively identified. But there is also a tension in the measurements themselves that suggests the universe may be hiding something. Two independent methods of measuring the current expansion rate of the universe, known as the Hubble constant, give significantly different answers. The first method uses the cosmic microwave background, measuring the detailed pattern of temperature fluctuations and fitting a cosmological model to them yields a Hubble constant of roughly 67 km per second per megaparsec. The second method uses a sequence of distance measurements within the local universe. The brightness of Cepheid variable stars calibrated against type Iria supernovae and yields a value closer to 73. These two numbers differ by roughly 9%, which is far more than the measurement uncertainties can explain. This discrepancy, called the Hubble tension, has persisted across many independent analyses and multiple teams. If it is real and not the result of some systematic error in either measurement chain, then the standard cosmological model is missing something. Possible explanations include unknown physics in the early universe that altered the expansion rate before recombination, additional light neutrino species beyond the three known, a form of dark energy that was stronger in the past, or effects from the large-scale structure of the universe that are not fully accounted for. None of the proposed solutions has yet achieved consensus. The tension may be the first solid observational signal of physics beyond the standard model of cosmology. Among the deepest anomalies within the observable universe is a region in the direction of the constellation Eridanus, an enormous void in the distribution of galaxies and matter, roughly 2 billion light-years across, associated with an unexplained cold region in the cosmic microwave background. Typical temperature fluctuations in the CMB are measured in tens of microkelvin. The Eridanus cold spot is colder by 70 microkelvin, statistically improbable under the standard cosmological model at a level that has drawn sustained attention for decades. The gravitational physics of a void this large produces a measurable effect on photons passing through it, a phenomenon called the integrated Sachs-Wolf effect. But the size of the Eridanus cold spot, if caused by this effect alone, requires a void so large that standard cosmological simulations struggle to produce it. Some physicists have proposed that the cold spot is an imprint from a collision with another universe during the inflationary epoch. Others have proposed that it is evidence against the existence of dark energy, that the apparent acceleration of cosmic expansion is an artifact of our galaxy being located near the center of an unusually large void. This is a minority position in cosmology, but it has not been ruled out. At the opposite extreme of cosmic phenomena, not vast and diffuse, but extraordinarily compact, lie the remnants of massive stars. When a star with a mass between roughly 8 and 20 times the mass of the Sun exhausts its nuclear fuel, gravity overwhelms the pressure that had supported it for millions or billions of years, and the core collapses in a fraction of a second. The outer layers are expelled in a supernova, one of the most energetic explosions in the universe, briefly outshining an entire galaxy of billions of stars. What remains is a neutron star, an object typically 12 to 15 kilometers across, containing more mass than the Sun, composed entirely of neutrons packed to nuclear density. Neutron stars are the most precise natural clocks known to exist. A rotating neutron star that beams radio waves from its magnetic poles sweeps that beam past Earth like a lighthouse, producing a pulse of radio emission with extraordinary regularity. These pulsars have been measured to maintain their rotation period with a stability rivaling the best atomic clocks built by human engineers. The first pulsar, discovered in 1967 by Jocelyn Bell Burnell, was initially designated LGM-1, Little Green Man, because the regularity of its signal was so unexpected that an artificial origin was briefly considered a genuine possibility. When two neutron stars orbit each other closely enough, they lose energy through the emission of gravitational waves, and their orbits spiral inward. Eventually, after millions or billions of years, they merge. This event, a kilonova, produces a brief, intensely bright explosion visible across billions of light years and synthesizes the heaviest elements in the periodic table: gold, platinum, uranium, iridium. For decades, astronomers debated where these heavy elements came from. Supernova explosions can produce elements up to iron efficiently, but elements heavier than iron require a different process, the rapid capture of neutrons by atomic nuclei, called the R process, which requires an environment of extreme neutron density. Neutron-star mergers provide exactly that environment. In 2017, the gravitational wave observatories LIGO and Virgo detected the merger of two neutron stars approximately 130 million light-years away, and within seconds, gamma-ray satellites, optical telescopes, and radio observatories around the world converged on the same location in the sky. What they found was a kilonova evolving in real time, the creation of heavy elements happening at a scale and in a place that could be directly observed. The gold in a wedding ring, the platinum in a catalytic converter, the iodine in the human thyroid. These atoms were forged in events like this one, scattered into space by the merger and eventually incorporated into molecular clouds, stellar systems, planets, and living things. Black holes represent the far end of the same continuum. When the collapsing core of a massive star exceeds roughly 3 solar masses, no force can halt the collapse, and the black hole forms. At the center of our own galaxy, behind the obscuring dust of the galactic plane, sits a supermassive black hole with a mass approximately 4 million times that of the Sun, designated Sagittarius A star. In 2019, the Event Horizon Telescope produced the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy Messier 87, some 6.5 billion solar masses, surrounded by the glowing ring of its accretion disk. The image confirmed predictions made by general relativity under the most extreme conditions yet tested. And black holes at the centers of galaxies can, under the right conditions, become something extraordinary. When large quantities of gas fall toward a supermassive black hole, the accretion disk grows intensely bright, so bright that the nucleus of the galaxy outshines the combined light of all its hundreds of billions of stars by a factor of hundreds or thousands. These objects are called quasars, and they represent the most luminous sustained phenomena in the universe. The quasar 3C 273, located roughly 2.5 billion light-years from Earth, is bright enough to be detected with an amateur telescope despite its enormous distance. At its peak luminosity, it emits roughly 4 trillion times the power of the Sun. The epoch of quasars coincides with the period roughly 2 to 4 billion years after the Big Bang, when the universe was densest and galactic mergers were most frequent, providing abundant fuel for active galactic nuclei. As gas was consumed and mergers became less common, most quasars faded. The supermassive black holes remain at the centers of galaxies, including our own, but now in a relatively quiescent state, surrounded by far less infalling material. Our galaxy's central black hole, Sagittarius A star, occasionally produces brief flares when small amounts of gas or disrupted stars fall toward it, but it is quiet by the standards of the quasar era. Over extremely long time scales, black holes are not permanent. Quantum mechanics predicts that they slowly radiate energy through Hawking radiation. For a black hole with the mass of the Sun, the complete evaporation would take approximately 10 to the power of 67 years. For the supermassive black holes at the centers of galaxies, the timescale is longer still. Deeper within a black hole than the event horizon, theory predicts a second boundary known as the Cauchy horizon. At this inner boundary, the equations of general relativity produce a breakdown in determinism. What happens to an infalling observer there is a matter of active theoretical dispute. The information paradox adds another layer of difficulty. If black holes eventually evaporate, and if Hawking radiation is truly thermal and carries no information about what fell in, then information is permanently lost, which conflicts with the foundational principle of quantum mechanics requiring that physical evolution always be reversible in principle. Resolving this paradox is considered one of the central problems in theoretical physics. The universe does not yield its deeper structure easily. Each answer arrives carrying new questions. But there is another set of questions that concern not what exists now, but what will exist in the distant future. Physicists who have thought carefully about the long-term fate of the cosmos have divided the future into broad epochs, separated by timescales so vast they require scientific notation to write. The current era, the one that has lasted for the past 13 billion years, in which stars are actively fusing hydrogen and lighting the universe, is called the Stelliferous era. It will continue for roughly 10 trillion years as progressively smaller and longer-lived red dwarf stars burn through their fuel. The last stars will flicker out roughly 100 trillion years from now. After that comes the degenerate era, lasting from 10 to the power of 15 years to roughly 10 to the power of 37. The universe will be populated by the cold remnants of dead stars. White dwarfs slowly cooling toward absolute zero, neutron stars and black holes. Isolated brown dwarfs drift through space, never having reached the temperature required to ignite fusion. The universe will be dark and cold, but not empty. The occasional collision between two white dwarfs may produce a brief stellar revival, a faint spark in the long darkness. By roughly 10 to the power of 40 years, proton decay, if it occurs on the time scale predicted by some grand unified theories, will have dissolved the atomic nuclei of all white dwarfs and neutron stars. All baryonic matter will have converted to radiation and lighter particles. The universe will be left with only black holes, the most durable structures, and a thin scattering of electrons, positrons, photons, and neutrinos. Then comes the black hole era, extending from roughly 10 to the power of 40 to 10 to the power of 100 years. Black holes slowly evaporate through Hawking radiation. The smallest evaporate first. The supermassive black holes at the centers of former galaxies hold out the longest, but eventually they too radiate away their last quanta of energy in a final burst of particles and light, and the universe is left with nothing but cold radiation, the photons and leptons of maximum entropy. And then, in infinite time, the fluctuations begin, the Boltzmann brain era opens. The long, dark, empty cosmos becomes the stage for the rarest of statistical accidents, and the stage in principle for everything to happen again. We speak of the universe as though it is a single thing, but the possibility that it is not, that our observable cosmos is one of an enormous or infinite number of separate regions, each with its own history and perhaps its own physical laws, has moved from the fringes of speculation toward the legitimate area of theoretical investigation. Inflationary theory naturally produces a phenomenon called eternal inflation. Inflation does not end simultaneously everywhere. It ends in one region while continuing in others, producing a universe like an endless foam, individual bubbles of completed inflation, embedded in a background of still expanding space, each bubble causally isolated from the others. Our observable universe would be the interior of one such bubble. Others exist unreachable, potentially infinite in number. If these other regions exist, the physical constants, the strength of gravity, the mass of the electron, the value of the cosmological constant, may take different values in different bubbles. Some bubbles would collapse immediately, others would expand forever, but never produce stable atoms. A small fraction might contain conditions compatible with complexity and with something capable of asking these questions. This is the landscape picture of theoretical physics, and it is deeply uncomfortable. If the constants of nature are not fixed by some fundamental principle, but selected from a vast range of possible values, then asking why they have the values they do may not have a derivable answer. The values might be what they are simply because they permit observers to exist. This connects directly to what physicists call the fine-tuning problem, one of the most debated topics at the boundary between physics and philosophy. The constants of nature appear to be adjusted to extraordinary precision in ways that permit the existence of stable atoms, stars, planets, and chemistry. If the strong nuclear force were a few % weaker, atomic nuclei would not hold together, and hydrogen would be the only element. A few % stronger, and all hydrogen would have fused into helium in the early universe, leaving no fuel for long-lived stars. The value of the cosmological constant, the one most difficult to explain, is fine-tuned to a degree that staggers even physicists accustomed to extreme numbers. If it were even slightly larger, the universe would have expanded too fast for galaxies to form. If negative and slightly larger in magnitude, it would have collapsed before stars could ignite. Whether this fine-tuning is evidence for a multiverse, for some deeper principle we have not yet discovered, or simply a reflection of the fact that we can only exist in a universe where we can exist. This question has no agreed answer and may not have one within the reach of current scientific methods. The Big Bounce hypothesis proposes that our universe emerged from the collapse of a previous one. Rather than treating the Big Bang as an absolute beginning, it describes a transition, one phase of an ongoing cycle. The mathematical framework of loop quantum cosmology supports the possibility of such a bounce by replacing the classical singularity with a quantum repulsion that prevents infinite compression. String theory approaches the same question from a different direction. In the framework of M theory, our universe may be a three-dimensional membrane moving through a higher dimensional space. The Big Bang would correspond to a collision between our brain and another. Other brains may exist, potentially generating new Big Bangs when collisions occur. This ekpyrotic scenario makes specific predictions about the spectrum of primordial gravitational waves, predictions that differ from those of standard inflation and that may be testable by future observatories. Gravitational waves themselves have opened a new channel of information about extreme cosmic events. Detected for the first time in 2015 by the LIGO observatories, they are ripples in the fabric of spacetime itself. The first detection corresponded to the merger of two black holes occurring over 1 billion light-years away. The collision lasted a fraction of a second, released more power than all the stars in the observable universe combined, and produced a distortion of space-time that, by the time it reached Earth, was smaller than 1,000th of the diameter of a proton. That we can detect such a signal at all is one of the more extraordinary achievements in the history of measurement. Gravitational waves pass through everything essentially unaffected, through planets, through galaxies, through the full depth of the observable universe. They carry a record of the most extreme dynamics in the cosmos. And if detectors become sensitive enough, the gravitational wave background produced by inflation itself may become detectable, a signal that would give us a window into the first moments of the universe that no optical or radio telescope can provide. Neutrino astronomy adds a third channel alongside electromagnetic observation and gravitational wave detection. Neutrinos interact so weakly with matter that they pass through the entire Earth with only a minuscule chance of interacting. The vast detectors buried under Antarctic ice or sunk beneath the Mediterranean ice cube and KM3 net can catch the rare collisions of high-energy neutrinos with atoms in their instrumented volume and trace those neutrinos back to their sources. The astrophysical sources of the most energetic neutrinos detected so far include active galactic nuclei and possibly the same type of events, cosmic ray accelerators, that produce the most energetic particles known to exist. What we are assembling slowly is a picture built from all these channels simultaneously, a multi-messenger astronomy in which the same event, a neutron star merger, a supernova, a gamma-ray burst is observed through gravitational waves, gamma rays, X-rays, optical light, radio emission, and neutrinos simultaneously. Each channel reveals a different physical process. Each adds a layer of understanding that none of the others can provide alone. This is not merely a technical achievement. It represents a fundamental change in how humanity relates to the cosmos. For most of history, the sky was accessible through one channel only: visible light. Every telescope ever pointed at the sky, from Galileo's to the largest optical observatories of the 20th century, was an instrument for collecting that one channel. The universe revealed by visible light is real and extraordinary, but it is like listening to a symphony with one's hearing reduced to a narrow band of frequencies. The full spectrum of what the cosmos is doing, the gravitational wave background, the neutrino flux from collapsing stellar cores, the X-ray emission from the hottest plasma in galaxy clusters, lies mostly outside what visible light can reveal. The universe that emerges from this accumulation of observations is stranger than the one any civilization has previously imagined, full of structures that challenge the concept of structure itself, governed by physics that breaks down at its own extremes, with a past and future that dissolve the ordinary notion of a story with a clear beginning and end, and with a size and age that render the words vast and old effectively meaningless as descriptors. Every major shift in the history of science has followed the same pattern. A comfortable certainty is replaced by a less comfortable but more accurate picture, which immediately reveals new uncertainties at its edges. The recognition that the Earth is spherical implied that people on the other side had to be standing upside down, relative to us strange, but true. The recognition that the Sun is not the center of the universe removed any special status from our location in the cosmos. The recognition that other galaxies exist revealed the universe not of hundreds of thousands of stars, but of hundreds of billions of galaxies. The recognition that space and time are not fixed, but shaped by matter and energy changed the meaning of the word reality. The next shift is already underway. Dark matter and dark energy together constitute 95% of the universe's content, and we have no confirmed understanding of either. The Hubble tension suggests the standard model of cosmology may be incomplete. The information paradox remains unresolved. The origin of the arrow of time connects the microscopic laws of physics to the largest structures in the cosmos in ways not yet fully understood. And the question of whether the universe is unique or one among an uncountable number of others. Whether the constants of nature are what they are by necessity or by selection remains entirely open. There is one more layer of strangeness worth examining, one that sits not at the scale of superclusters or black holes, but at the level of the very act of observation itself. Quantum mechanics, the framework that describes the behavior of matter and energy at the smallest scales, is the most precisely tested theory in the history of science. Its predictions have been verified to more than 10 decimal places in some cases. And yet it contains at its core a problem that has been debated since the theory was first formulated in the 1920s, and that remains unresolved to this day. In quantum mechanics, a physical system is described not by a definite state but by a wave function, a mathematical object that encodes the probabilities of finding the system in various possible states when it is measured. Before measurement, the particle exists in a superposition, a combination of multiple possibilities simultaneously. When a measurement is performed, the wave function collapses to a single definite outcome. The system resolves from a distribution of possibilities into a single fact. But what counts as a measurement? What is the physical mechanism by which the wave function collapses? The theory does not say its equations describe the evolution of the wave function with perfect precision, but they do not describe the collapse. The collapse is imposed by hand, as an additional postulate, without any underlying physical explanation. This is the quantum measurement problem, and its relevance to cosmology is direct. The universe itself began as a quantum system. The fluctuations in the early universe that seeded all subsequent structure, all the galaxies, superclusters, and voids that exist today, were quantum fluctuations, imprinted in the first moments after the Big Bang and stretched to macroscopic scales by inflation. In some sense, the largest structures in the observable universe are the classical remnants of quantum events. They exist because quantum superpositions were somehow resolved into definite configurations. But how? In a universe that was initially entirely quantum mechanical, with no external observer to perform a measurement, what caused the wave function of the primordial fluctuations to collapse into the specific pattern of density variations that became the seeds of galaxies? The most widely accepted partial answer involves a process called decoherence, the irreversible entanglement of a quantum system with its environment, which suppresses quantum interference and makes the system behave as though it has a definite classical state. But decoherence, as physicists understand it, does not in itself eliminate the other branches of the wave function. It merely makes them inaccessible and non-interfering from the perspective of any local observer. The question of what is ultimately real, whether the other branches still exist in some sense, remains a matter of genuine theoretical dispute. The many worlds interpretation of quantum mechanics formulated by Hugh Everett in 1957 takes the most radical possible position. It denies that the wave function ever collapses. Every time a quantum event occurs with multiple possible outcomes, all outcomes happen in different branches of a universal wave function that never collapses and never reduces. The universe constantly splits in this picture into an ever-growing number of equally real branches, each one containing a slightly different history. An observer in any one branch experiences only their own branch, but every other outcome has also happened somewhere in the branching structure of quantum reality. The many worlds interpretation is deeply uncomfortable, not because it is internally inconsistent, but because of its implications. It implies an unimaginably vast proliferation of parallel histories, most differing from our own by only microscopic details, others diverging sharply at macroscopic decision points. It provides no mechanism by which the probabilities of different outcomes can be derived from first principles that satisfy everyone. And it offers no possibility of ever verifying the existence of the other branches, because by definition they are causally disconnected from ours. Yet, in the context of cosmology, it has a certain uncomfortable plausibility. A universe that began as a quantum system with no external observer that evolved through quantum processes to produce a classical world we inhabit. This is precisely the situation where an interpretation that never requires an external observer becomes attractive. Cosmological quantum mechanics and the measurement problem intersect in ways that force the question of interpretation out of abstract philosophy and into the domain of empirical science, not because the branches can be observed, but because different interpretations make different predictions about the statistical properties of the quantum fluctuations that seeded the large-scale structure of the universe. Stars are the engines that translate the abstract architecture of cosmology into the specific chemistry that makes planets and life possible. The Big Bang produced almost exclusively hydrogen and helium, the two lightest elements, along with trace amounts of lithium and beryllium. Every heavier element in the periodic table, carbon, oxygen, iron, calcium, silicon, nitrogen, was forged inside stars and distributed through the cosmos by stellar death. Without stars, the universe would contain no chemistry. Without chemistry, no planets. Without planets, no surface on which the slow process of self-replicating molecules could organize into something capable of looking up and asking questions. Stars are not simple objects. They are sustained by a precise balance between the inward pull of gravity and the outward pressure generated by nuclear fusion in the core. As long as hydrogen fuel is available in the core, this balance holds and the star sits on what astronomers call the main sequence, a stable configuration that may persist for millions to billions of years depending on the star's mass. The most massive stars burn through their fuel in a few million years, progressing through increasingly heavy elements: hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron, before the production of iron consumes rather than releases energy and the core collapses catastrophically. The Sun, a medium-mass star, will remain on the main sequence for roughly 5 billion more years. When its hydrogen runs out, it will expand into a red giant, its outer layer swelling to engulf the inner planets of the solar system, before eventually shedding those layers into a planetary nebula and leaving behind a white dwarf, a crystallized sphere of carbon and oxygen, roughly the size of the Earth, slowly cooling over trillions of years. In the far future of our own galactic neighborhood, another event of cosmic significance is scheduled to occur. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, located approximately 2.5 million light-years away, is approaching us. The two galaxies are moving toward each other at roughly 110 kilometers per second, and in approximately 4.5 billion years they will collide. The merger will not be a violent collision in any intuitive sense. The distances between individual stars are so vast that direct stellar collisions will be rare. But the structure of both galaxies will be profoundly disrupted. Over hundreds of millions of years following the initial encounter, the two galaxies will merge into a single large elliptical system, provisionally called Milkomeda or Milkdromeda by those who have modeled the event. The Sun, if it still exists, may find itself in a completely different region of the merged galaxy, far from its current position in the Milky Way's Orion arm. In recent years, the universe has offered a new and still puzzling phenomenon for astronomers to investigate. Fast radio bursts, extraordinarily brief, intensely energetic pulses of radio waves, lasting only milliseconds, detected from cosmological distances, were first identified in archival data in 2007 and have since been catalogued in growing numbers by radio telescopes sensitive enough to detect them in real time. Their origin is not fully understood. The leading hypothesis attributes most of them to magnetars, neutron stars with extraordinarily powerful magnetic fields capable of releasing enormous amounts of energy in brief flares. But the diversity of observed fast radio bursts, including the discovery of sources that repeat and sources that do not, suggests that more than one physical mechanism may be responsible. Fast radio bursts traverse enormous distances, and as they do, their constituent frequencies are dispersed by the ionized gas of intergalactic space, higher frequencies arrive slightly before lower ones, and the magnitude of the delay carries information about the total amount of ionized material the burst passed through. This dispersion measure can be used to estimate the distance to the burst and also to probe the distribution of matter in the intergalactic medium in ways that complement other observational methods. In this sense, fast radio bursts function as probes of cosmic structure, providing data about regions of the universe that are otherwise difficult to study. What connects all of these phenomena, the statistical mechanics of infinite time, the acoustic imprints of sound waves frozen in the early universe, the gravitational flows of superclusters, the cold anomaly in the microwave background, the evaporation of black holes, the synthesis of gold in neutron star mergers, the quantum fluctuations that became the seeds of galaxies, the upcoming merger of two galaxies, the puzzling bursts of radio energy from unknown sources at cosmological distances, is the recognition that the universe is a single, deeply interconnected system, operating across an enormous range of scales in space and time, and that understanding it requires simultaneously the physics of the smallest particles and the geometry of the largest structures. No single observation explains it. No single theory captures it all. What we have is a growing network of constraints, measurements that must be mutually consistent, theoretical frameworks that must account for all the data, anomalies that resist explanation and demand either new observations or new physics. Science in this domain proceeds not by revelation, but by the slow accumulation of evidence, the construction of models, the identification of tensions and contradictions, and the gradual narrowing of the range of possibilities. Every generation of astronomers and physicists has inherited a universe that seemed, at the time, nearly comprehensible, and has bequeathed to the next a universe revealed to be stranger and larger than previously suspected. There is no reason to think this process is approaching an end. The instruments of the coming decades, space-based gravitational wave observatories, enormous ground-based optical telescopes with mirror diameters of 30 meters, neutrino detectors of unprecedented sensitivity, cosmic microwave background experiments sensitive to the polarization signature of primordial gravitational waves, will reveal things that are not yet anticipated, answer questions that are not yet fully formed, and generate new puzzles whose nature we cannot currently predict. There is a possibility so extreme that physicists who discuss it typically do so with a kind of careful understatement, as though the magnitude of the consequence makes ordinary alarm seem inadequate. It concerns the stability of the vacuum itself, the ground state of space. According to the standard model of particle physics, the Higgs field, the field responsible for giving fundamental particles their mass, permeates all of space at a specific value. That value corresponds to the vacuum state, the lowest energy configuration of the field. But measurements of the Higgs boson mass and the top quark mass, conducted with increasing precision at the Large Hadron Collider, suggest that this vacuum state may not be the true minimum energy state of the Higgs field. It may instead be a metastable state, a local minimum, rather than a global one. Imagine a ball resting in a shallow depression on a slope. It appears stable. It is stable against small perturbations. But it is not at the lowest possible point on the landscape. Given enough perturbation, or given quantum tunneling, which allows transitions that are classically forbidden, the ball could shift to the lower valley. If the Higgs vacuum is metastable, then quantum mechanics predicts that somewhere, at some random point in space, a bubble of true vacuum could spontaneously nucleate. Inside that bubble, the Higgs field would settle to its true ground state with different values for the constants of physics, different particle masses, different interaction strengths, a fundamentally different set of physical laws. The wall of that bubble would expand outward at the speed of light. Everything it encountered, matter, radiation, atomic structure, chemistry, all the complexity that the current vacuum permits, would cease to exist in any recognizable form. The bubble would be invisible in advance of its arrival, because it travels at the speed of light and no signal can precede it. Current calculations suggest that if the vacuum is indeed metastable, the expected lifetime before such a nucleation event is vastly longer than the current age of the universe, likely longer even than the timescales of proton decay and black hole evaporation. The probability in any given moment is incomprehensibly small. But in an infinite universe operating for infinite time, the expected number of such events is not small. It is infinite. This does not mean vacuum decay will happen here or soon. It means that in the full ensemble of space-time, regions of false vacuum will eventually transition to true vacuum in an endless progression of expanding bubbles, each one erasing everything in its interior and leaving behind a universe operating under different rules. There is also a particle that permeates the universe in extraordinary numbers, that passes through matter with almost perfect indifference, and that has repeatedly surprised physicists by being slightly more complicated than expected. The neutrino, first predicted by Wolfgang Pauli in 1930 to account for missing energy in radioactive beta decay and not directly detected until 1956, is produced in enormous quantities by nuclear reactions in stellar cores. Every second, approximately 65 billion solar neutrinos pass through every square centimeter of the Earth's surface facing the Sun. They pass through the Earth itself with negligible interaction. Most of them pass through your body right now, without any physical effect whatsoever. For decades, neutrinos were assumed to be massless, traveling at exactly the speed of light and carrying no mass to speak of. Then came the solar neutrino problem. Experiments designed to count the neutrinos arriving from the Sun consistently found fewer than the solar model predicted. Either the model of the Sun was wrong, or something was happening to the neutrinos on their way from the solar core to the detector. The resolution, confirmed in the late 1990s by the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada, was that neutrinos oscillate. They change from one type to another as they travel, cycling between the electron neutrino, the muon neutrino, and the tau neutrino. This oscillation is only possible if neutrinos have mass, however small. The discovery that neutrinos have mass had immediate cosmological implications. Neutrinos were produced in vast quantities in the Big Bang and remain abundant throughout the universe. With roughly 336 cosmic background neutrinos per cubic centimeter of space, comparable in number density to the photons of the cosmic microwave background, even a tiny mass per neutrino translates, when multiplied by their enormous abundance, into a significant contribution to the total mass energy of the universe. Neutrino masses are small enough that they do not dominate the mass budget. Dark matter is a far larger contributor, but large enough to influence the fine details of the large-scale structure of the cosmos. The precise value of the neutrino mass remains one of the open measurements in particle physics, constrained by cosmological observations, but not yet pinned down from first principles. The most energetic individual particles detected in the universe are not photons or neutrinos, but cosmic rays, protons, and heavier atomic nuclei accelerated to energies far exceeding anything achievable by terrestrial particle accelerators. The Pierre Auger Observatory in Argentina, a detector array covering 3,000 square kilometers of the Argentine Pampa, detects the cascades of secondary particles produced when ultra-high energy cosmic rays strike atoms in the upper atmosphere. The most energetic events correspond to primary particles carrying energies of tens of joules, an amount of energy that concentrated in a single subatomic particle defies ordinary intuition. A proton moving at that speed carries as much kinetic energy as a tennis ball served at moderate pace, all packed into an object 10 to the power of negative 15 meters across. Where cosmic rays at these extreme energies come from remains an active question. The universe is effectively opaque to the most energetic cosmic rays at sufficiently high energy. Protons interact with photons of the cosmic microwave background and lose energy rapidly over distances of tens of millions of light years. This means the sources of the most extreme cosmic rays must be relatively nearby on cosmological scales. The leading candidates are the most powerful accelerating environments known: the relativistic jets of active galactic nuclei, the magnetospheres of rapidly rotating neutron stars, and the shock waves of galaxy cluster mergers. Identifying the precise sources requires measuring the arrival directions of cosmic rays and correlating them with known astrophysical objects, a project that has yielded tantalizing hints of correlations with starburst galaxies and active galactic nuclei, but not yet a definitive identification. The same sky that humans have watched for 10,000 years is still, in every meaningful sense, deeply unknown, and that, perhaps more than any single discovery, is the most remarkable thing about it.